see. And it's going to be display capture. Figured I don't want to use that. I want to use a Windows capture. Huh. Okay, so let me see. I think it's a few more clicks and then oh yeah, this is the reason. Weak. Why is not willing to show this weak PowerPoint presentation? Of course, I always can go like just to display my screen, but I would like to cancel. Let's not use this.
By the way, you still didn't give me the possibility to edit the PowerPoint. The one that
Really?
you sent me last night. Yes.
Ah, how come not?
It was just viewing.
Viewing. Okay, so let me see if I put this in a presentation mode, how it's going to be. How it appears. So it comes with a little bit of delay.
No, it's fine.
No, it's not fine. Let me see.
Is it in Power?
Yeah, it should be like
Nah.
full screen already.
So have you shared the screen or just the PowerPoint?
Because the OBS is not willing to sum, so it's a window capture that it's doing. So should I instead using the display capture?
So can you try it with display capture?
Okay, so let's try this one.
No,
Yeah,
it's
that's better. That's much better. Okay, last thing is this one.
Can you stand up so
Uh,
I can adjust your height?
What's that?
Can you stand up so I can adjust your
Sure,
height?
sure. I'm gonna just put this one on. This guy got stuck.
I believe it's fine. What do you think?
I don't see this by myself. Yeah, looks good. Looks really good. Looks good.
You haven't started sharing on the project.
Yep. PC2.
Shouldn't it be the doc 2? Because yeah, PC2, this one.
So it's a funny thing that each of these lecture rooms, they must have a different kind of system. So there's kind of funny. Okay, so we have everything on except this is not yet on. We need to do something like, what else?
Usually it was fine.
Can you try to, because I'm gonna take a look at this.
Restart it. Okay.
So that one,
Yes.
start. This is number 2.
Yes, PC2.
Projector, screen. But still nothing comes. Is it all the televisions are off? This is on. Are these firing up too? These projectors. Okay, online participants, we're still not able to get started as we are not able to display my screen to online, I mean the participants that are here in the lecture room. I think that we did nothing differently than last time.
It says no signal.
No signal. This is really annoying.
Have you duplicated the picture?
You think that could make a difference?
Usually there was some problem.
Okay, so let's try this. Let me take it off. Put it back. Oh, I see that it's now blinking. And this guy is blinking too. Okay, so we have all except projectors on.
At least all the television they works.
All televisions are okay.
Yeah.
But how can I put this? You guys, can you live without these projectors if we just have televisions on? Would that be okay? This one.
There are four basically working now.
4. Okay, one more thing. I can do this. Duplicate. Duplicate is the way to go. All right, so I think that I can put the window capture on like this. Okay, guys, would it be okay if we get started? I'm unable today, for some reason which I don't understand at all, I'm unable to put these projectors on. So you cannot see what's going on in sidewise, but you can see it in the televisions. Is that okay? All right, so again, do you mind if we go again in the same way we started 2 weeks back? So it's going to be my rehearsal and your feedback, and each of the feedback is worth of 1 point, 1 extra point. Okay? Hold on. So I just need to find like, it's a timer.
I have a question.
Yes,
Is it will be like online presentation or offline presentation?
this is going to be online presentation. So it's going to be using this system, which is like Cisco system, a little different than we typically use it, but it is an online interview. And the interview is getting started by my 5-minute introduction about what is me and what is my project about. And then there's going to be 20 minutes real questions and answers. Okay, but let me put this on. So it's going to be in my next rehearsal. So I haven't practiced this since we met 2 weeks back. Oh, not this one. I don't want to use this presentation mode, but I want to use instead, I want to use this one. Aki,
Here it's not
Mikko,
in full screen mode. I believe that you picked the wrong one.
so it's what?
It's not on the presentation mode. In OBS, I believe you picked the wrong choice again, wrong option again.
All right, so one more time. OBS is a bit more complicated than anything else. Yeah, I'm using window. I wanted to use a display capture instead. Okay. I need to do this one more time. Sorry about this, guys. Okay. Okay, so it's perfect. Aki, Multibody, Mikkola, LUT University. I'm helping people to better understand dynamics. I started my career already more than 30 years ago, as can be seen this television capture where I'm introducing to in Finnish science television how to use a computational dynamics to predict loadings in hydraulically driven systems. And this kind of studies were something that we helped to make a better design in heavy machinery. Today, I wanted to introduce you a project that is taking all my previous developments and putting them together to build a better understanding about how is that we can build more fatigue-resistant structures. Since this television show, I've been studying with the formulations of multi-body system dynamics, including more efficient formulation in flexible bodies, real-time simulation, and how to combine hydraulic actuators models to the multi-body system dynamics. But as a major trend, there is a desire to build heavy machinery to be more lightweight. And the easiest way to make that happen is to use a high-strength steel. High-strength steel can handle the higher loading than conventional steel, but comes with a big problem. And the big problem is that dynamics becomes to be more significant. As can be seen here in a cantilever beam, you can make the structures to be more slender, and you can load it, or you can handle the same amount of mass when using high-strength steel comparing the conventional steel. Now, as you can see, the cantilever beam that is green in a color, deformation becomes to be more significant, and the dynamic behavior becomes to be more cumbersome to deal with. Now, typically, when you're building the heavy machinery, you're combining components together using welding. Welding comes with the problem that due to the welding process, there's going to be initial cracks and high residual stresses. Once you know the material, which is going to be steel here, and geometries of the joint, and the loading, you can make a prediction of fatigue life. What's the hardest is going to be knowing the stress history. And this project will introduce a concept that helps to create a more better understanding about stress histories that are loading the joints in heavy machinery. So as mentioned, I've been working with multiple different formulations within the multi-body system dynamics. Like shown in left side of this slide, I've been dealing with the floating frame reference formulation that helps to create more accurate description of flexible bodies. This is a very critical component needed in this project too, and I need to take this floating frame reference formulation to another level by making more accurate description of modes that could be based on mixed finite element method. Hydraulics, as can be seen here, can be modeled by technique that we have developed in LUT University a while ago, and the interaction with the environment, it's going to be based on particle dynamics and high-field technology. Now, all these can be put together and it can be solved in real time, as can be seen here in this animation. Now, this animation comes, or this simulation comes with a major drawback that is associated with the fact that all the bodies are assumed to be rigid, making it not possible to predict accurate loadings and stress histories that are imposed to the welded joints. So what I wanted to do is, instead of using rigid bodies, I want to use a flexible multi-body dynamics. I want to do this to make a better prediction about fatigue life prediction. My final objective of the project is to make this to be embedded solution that instead of using real-time simulation model, we are reading the sensor signals from actual machines, and based on the sensor signals from actual machines, we are operating or we actuating the simulation model, and that makes it possible to kind of have like a mileage sensor that tells how much mileage is left before the structures are fully destroyed in terms of fatigue. So my project is aiming to this kind of embedded system that makes a better use of high-strength steel and allows to build the more lightweight structures. Thank you. 4 minutes and 50 seconds.
Like 440.
440.
Yes.
Okay. All right. Now, you want to get your improvement proposals via emails, or you want to tell me during the break? Up to you. You can tell me right now if you want.
Yeah, like there are a few things.
Few things, I know.
So first of all, the introduction section. I don't like the idea that the video finishes and you continue and.
Okay, so that's not well coordinated.
Yes.
Okay, so when the video stopped? It was a while ago.
It's like, you know, if you could adjust it just to finish it before the video ends or at the same time.
Same time.
Yeah.
Okay, that's clear.
You can do the video like start from the start, like a loop one.
So the video could get started a little later.
No, like make the video like loop. So.
Oh, okay. So that's one thing. Okay, I'm gonna make a new notes here. So that's, and of course, Mustafa, can you give a points?
Oh, okay. Just send
Okay.
me an email.
Yeah. Okay, so the video is not matched.
And on 4th slide, there is this red lines, and when the video starts, there is like.
Days here.
Yeah, it's
Yeah,
not.
I have a major comment on that. I believe that you have to change that slide somehow.
What should I do there? Here.
You can add elements.
So I can what?
Add elements like, I don't know, like either using those.
Okay, what if I'm gonna coordinate this in a way that I
We can play that one in the separate slide.
Yeah.
like what?
The video is playing in a separate slide, but the methods that you are describing, that one is the picture.
Oh, okay, what about this? What if I'm gonna put this, because I think what bothers a little bit is these lines here.
Yeah, like you can just try to attach them to the picture instead of just to the points.
Okay, so what about if I do this? Like this, each of these lines appears at certain time, comes and goes. They comes and goes.
Yeah.
Like here is a mechanics, and I'm gonna time it in a way that okay, this is showing the mechanics, and the next one,
Yeah.
these are too high risk.
I think that you shouldn't make it like it's on time.
Maybe just
Okay.
start.
If that's the timer, it will be lost. But
So if the timing is not good, then it's gonna be very chaotic. Okay, so what are you proposing then?
So I think you can do like an animation for the lines, and when you start the video, they will disappear.
Yeah, I got it. So in a way that I say, as soon as I click this one, I can put this to be automated timing. As soon as I click this one, these
They disappear. Yeah.
they disappear.
Yeah. So I think you
Can
just
I
need to
can I
collect
do
the
something
lines.
like that in a PowerPoint? Yes, I can.
You could collect them and then you do animation and then.
Yeah, I got it. Yeah,
So
can I do something like that in?
let us agree that there is a problem regarding these slides. We're gonna discuss on how to be changed.
All right, yeah. So but now there is an equations.
Yeah, like about that. That's the thing. I believe that the best course of action would be, because based on what I can see, each equation is about one part. Like one is about hydraulics, the other one is about other
Yeah.
things. I think that if you use some kind of magnifier, it would be better. That's, you know,
Okay. So it's something like highlighting this part.
yeah, I can do that for you.
Okay.
Let's discuss it later.
Okay.
So about the second slide,
one?
third slide.
Third
It's
one.
method.
This is what you helped me to put
Yeah,
together.
like it's about the presentation. So you know, it would be good if you explain why we should change to lighter material at all.
Yeah.
because based on the project that we have, there
Yeah.
are still many companies that they think that okay, why lighter material?
Yeah. Okay. Right. Okay. So why lightweight?
Yeah.
Because like the weight is related to energy consumption and how much damage you can
Sustainability,
introduce in nature and stuff like that. But we're not mentioned.
Yes.
Why lightweight?
Yes.
Okay. Okay.
And,
What
you know,
else?
Mentioning the lightweight could be that your hooking point to grab the attention.
Okay. All right. What do you guys like about this slide? I was thinking that would this be better to be like similar than the first slide, like this kind of like round shape here? Because this is the one that is destroyed.
I think it's better.
Yeah.
But that would be better. Okay, what about this?
Does the slides have to be black?
No.
I think especially in the next slide, it's really weird that the formulas are with a white background and then the rest of the slides black.
Yeah, this is a good question because this is LUT PowerPoint template.
You can change, like we can change it, make the equation in white.
Or it can be
Yeah,
like
maybe
add
it's
the
better.
white part, like here, just to make a white part only for this.
Okay. All right, but you don't like this black one.
Yeah.
They don't like the contrast.
I think it's
They don't like the contrast.
on the first three slides, pretty good, but then it's going like the equation is going white, and the next slide is white at all. So
Yeah.
it's a little bit not.
Yeah, that is correct. So it's not consistent.
Yeah.
So it's not consistent. Okay. Yes. Yes, sir.
In the video part of the fourth slide,
This one.
yeah, another solution could be that you made a video with the formula inside of the video, so you can
Oh, like kind of like they comes like pops ups and
yeah,
during the animation.
yeah, but a whole video with the formulas, so you can make also the video more bigger.
Okay. All right. Yeah, that could be the one thing to do too. All right, guys, can you send an email to Mustafa and make a request about these extra points? Seriously, it's because I appreciate this. It's you guys know that this is a big deal to me. That's why I'm practicing this.
And also, when it's a video, like online, and the hand in a pocket, it
Oh,
looks
yeah.
like it's cutted.
You had your hand in
Yeah.
your pocket.
Was it?
Yeah,
on
yeah.
one
So
part.
you saw that?
Yeah.
Ah, not good. Not
So
cool.
Are you going to give the presentation standing? That's the thing.
I guess, because I have my table that I can put it in upright position like.
Because I
But
thought that it's
standing,
going
the
to be like-
hands in the pocket is no good, absolutely no good at all. Because it's my body language is that I don't care. I don't care about this funding. I don't respect you guys. This is not the way to go. Good point. Like this one,
Yeah.
absolutely not. Yeah. And it's not relaxed in that sense. A lot of good points. Okay, so let's discuss. Yeah, thank you. Appreciate this. Sorry to take your time. But you're going to get posted. Yeah, we'll let you know how things are here, progressing here because it's going to be in 18th of March. So it's more than a month from now, the interviews. And then results. Yeah, it's going to be sometimes, I think, after summer break. So you are no longer in this class, but I will let you know anyways, regardless what's going to be the final outcome. Okay, but good point. I have my next practice with the people in my lab on Monday. Okay, but now something a little different then. Something a little different is this. Okay, just want to make sure that this displays well to you here and here. All right. Okay, what we're going to do today, we're going to continue with the finite element discussion. There's actually multiple things to discuss, but we're going to cut the corners a little bit. So once I'm done with this element technology, that once you guys understand that the elements is not about, just the nodes, but it's all about what's between the nodes and how you can predict the behavior between the nodes, then we're going to move on rapidly all the way to equation of motion that is based on finite-element method. Equation based on finite-element method is like almost like equation based on multi-body system dynamics with major difference. And the major difference is this. Typically, finite-element method is meant to be designed for small rotation. So they cannot handle, as conventional finite-element method, large rotation. Of course, there are extensions of finite-element method to take large rotations into account, like large vector formulation, large rotation vector formulation. This is one thing you can use an incremental approach, but as a general conventional finite element method is meant to be for something where the deformation is small and rotation with respect to reference frame is small as well, which is okay if we're going to combine these to multi-body system dynamics, and it's going to be okay because the large rotation will be handled by reference frame, where the description is based on multi-body system dynamics. Anyways, so like I said, so once we are done with the element technology, we rapidly going to move on to equation of motion. And then we need something that is extremely critical for us. Something very critical for us is going to be modal reduction. That's needed. Otherwise, this is not going to be a practical solution at all. Now, what is this modal reduction? This is where we're going to take a step in the direction of Jussi Sopanen. Because Jussi Sopanen is moving from one space to another space, we too need to make one step in that direction. So we need to move from nodal space to modal space. Now this is something that I guess is already sounds familiar to you, particularly if you have participated in Jussi's class. Jussi is telling all about this modal space and other spaces. We're going to make one step in this direction. And it's also important because it takes us to vibration problem. And we're going to look at the eigenvalue analysis, something that is very common in vibration analysis. Okay, all right, so, but before that, short summary. How was a finite element method? Finite element method is coming from the polynomial expansion. This is like a little bit extreme statement, but like the soul of the finite element method comes from the polynomials. But there are alternatives for conventional finite element method where the polynomials are replaced by something else, like NURBS. NURBS, which is non-uniform rational B-splines. And the NURBS are the technology behind the CAD software. And the CAD software are all based on NURBS. So it was like non-uniform rational B, this is B splines. Each of the CAD software, they're using NURBS technology. Now, there are extensions of finite element method that instead of using polynomials, you're using NURBS. And that gives some advantages that the meshing is going to be more convenient. Here, we are not going to dodge that. So we're going to just stay in a polynomials. And it's kind of simple thing. You're selecting the order of polynomial, component of the polynomial expansion based on the number of degrees of freedom. That's basically what you need to do. And you can select these polynomials in order, or you can do this, you can skip some of them. If you skip some of them, you get non-conformal elements that may or may not perform better than the ones that are selected in row. Okay, so what happens once you get the polynomial expansion? Then you make use of the information you have in your element. Like here, for example, you have two nodes, and they can move left and right in each of the location. Once you introduce this information to your polynomials, you will get relation between the nodal degrees of freedom and polynomial coefficients. And now what I wanted to do is that I wanted to solve these polynomial coefficients like I did here, substituted back here, and I'm going to get something that is called safe functions. Safe functions tells me what kind of the deformation one element can capture. That's what it is. But this is like a piece of the solution. And when you keep on adding these pieces of the solution, you will get the entire solution of your structure under investigation. That's how it goes. So it's a piece by solution. Like here, is a linear polynomials, a linear polynomial expansion, and the safe functions are linear. So it's like each of the, so if you, for example, have these two nodes, you move this one here, each of the particles between, they're going to move with respect to, using this kind of the lines. So they're moving linearly. This is a little hard to understand, but if we're going to look at the same, but using the beam elements, where the beam elements consist of two nodes, node 1 and node 2, and this has a transverse direction and rotation, transverse direction and rotation, so we only look like off-plane deformation like this. Now I have 4 degrees of freedom, so I can select my polynomials such that it consists of 4 components. So these are my 4 components. And again, using the same technique that I use in a spring element, I can get the safe functions. This is how they look. This is what the one element is capable of. A very important observation is this. Safe functions are orthogonal. So they're affecting 1 nodal degrees of freedom at the time. Only 1. But they still predict particles between the nodes. Example is here. This one here express if you have a unit displacement in a first node y direction. You see that it is actually moving 1 unit in a y direction, but the angle here is not changed at all. Here, the angle is not changed, and the displacement is 0. So all other components of the nodal degrees of freedom are not affected at all. They are affected in the middle of the element, but this is telling the way the element can deform. The same here. Now this is a rotation. Displacement here is 0, displacement here is 0, and also the angle here is 0. And then the ones that are symmetrical related to node number 2. Now, how is it going to be different? Like I said, that sometimes you can skip some of the polynomials and not select them in order. So now what I did was that instead of selecting here x power 2, I'm selecting x power 3. And here, instead of x power 3, I have x power 5. So this is non-conforming element. So what's the consequence of that? Well, the safe functions look different now. They still have this ability to be orthogonal. It must be like that. They still are orthogonal, but you see the deformation is more like, how can I describe this? More like exaggerated a little bit. So they are more heavier deformation than it would be otherwise. So that's a consequence of making selection like this. Which one is better? This is a little hard to know. But as a general note, most of the non-conforming element tends to have a little better convergence rate. Convergence rate was, again, this rate, like how many elements you need to get acceptable solution. How fast you reach acceptable solution. Sometimes you can boost this efficiency by using non-conforming elements. But the problem is, sometimes what can happen as a consequence is that the convergence is no longer one side, but it can even vibrate like this. This is not very good, but it's still acceptable, but it's not necessarily the optimal way of convergence. And why not? Because each of the finite element you do, you should actually check whether or not your solution is converged. Because you may get the solution that is here that is way off, really way off. Now this is simply way off because amount of elements you have used is not sufficient. It's not sufficient. So what you should do is that you should mesh your structure by 2 different alternatives, less and more elements, and if the solution is not changed, it's obviously converged. But if it is changing, you keep on increasing the elements until it's not changing anymore. But now you look at this non-conforming element, if you really have a bad luck, you can get this one here and this one here, and it looks that it's converged, which is not the case, because it's not approaching from the one side only. And this is something that makes things a bit more complicated. Okay, so that's a polynomial. So this, again, comparison about different safe functions. They're just different safe functions. But this is the soul of finite element method. That's what the finite element method is about. Remember, I said that we have these nodal locations. But more important than the nodal location is to know where each of the particles are traveling. This is an information we must have to be able to create the stiffness matrix and other components. All right, physical interpretation of shape functions. Let me think if I explain these to you clear enough. All right, so the way that an element can deform defines the rotation of the particle. Okay, this is something that we have learned earlier. Rotation of the particle is something that we have discussed a lot. Defines the strain displacement relationship. No clear interpretation. Yes, I have explained this clearly, so you should have an information to be able to answer this. And Socrates is on, so go ahead and enter your answer. And how is it, guys? Do you still have this WhatsApp group? No? Are you not planning to establish one, or what's up with you? Because what they did in our last class was that they organized a WhatsApp group, and every single time there was in-class quiz like this, there was a lot of communication, like, I know what's the correct answer. I know the correct answer is D, so trust me, I know what I'm doing. So vote for D. And this was the way that their scoring was pretty high, actually. And I'm thinking that was the reason. You think? Hard to say. Hard to say. Okay. But you see that Socrates is on. Is not on? Not on. Okay, okay. Did you guys use LUT, room number LUT2? Why? Okay, so let me see. Okay, so it's why? Back online. What is this? Sorry about this. I need to. It was a wrong room. It was altogether wrong room. So finish activity. It's going to be this one. Teacher. Okay. Okay, is it visible now?
Yes.
You guys don't see there. I don't know if there's anything to see here, but I'm guessing that what we're going to do is that now once you have the access to this, sorry guys that I can see that the option option B is different here than it is in my PowerPoint slide, but it's incorrect anyway, so it doesn't make much of a difference. So there's only 3 options left. Okay, so don't vote for B, please. And I'm going to take myself back here. And then, like we did the previous 2 weeks back, so once you have an information about, it's like almost like kinematics. That's what the shape functions are. And then you're good to go, and then you're ready to derive this stiffness matrix, and then you can define the mass matrix too. Okay, so let's take a look briefly. We're not going to spend too much time to do this, so we're going to just cut the corners a little bit and make it equation of motion, which is inertial forces, elastic forces, and external applied forces. So difference comparing what it was earlier, that elastic forces was not there. Elastic forces is stiffness matrix multiplied by nodal displacements. Okay. All right, so here it is. So here's a relation between the strain in axial direction and slope in transverse direction. And this relation, where's my pen here, is written here. So this is the kind of like the way that you can know like how is the displacement of the particle, because what you do here is that once you have the midline of the element like this, you're comparing the perpendicular direction of the midline. Here it is. And now this is telling you like further you go off from the midline, the bigger your strain, if it is non-zero. Because if it is originally, let me make a magnification here. So the situation is like this. So here's your midline, this is your cross section, original is here, and this is a displacement. This one, this guy. That's what it is. And we do know, based on what we discussed earlier, that the strain can be defined in a way that if there's a displacement this direction, difference with respect to x, that's what it is. Now substituting this information here, you can finally create the relation between the displacement and strain. Displacement and strain, that's something that I mentioned earlier, is called kinematic matrix. And you can get at this by differentiating this particular case, differentiating this shape functions twice with respect to x coordinate axis here. That's how you can get it. Once you do it, it's going to read like this. Okay, this is pretty much the most cumbersome thing to do. And again, it's differentiating the shape functions twice with respect to x-axis. Very easy to do if you're using symbolic math tool. Okay, that's going to be your kinematic matrix. And now with help of your kinematic matrix, you can build your stiffness matrix. Stiffness matrix is telling you how much element is resisting the forces. If there is a force, how much they're resisting the forces in each of the degrees of freedom that are associated to nodes. So that's what it is. So that's what the stiffness matrix is. It's like, I understand where this typical teaching is coming, that it's like spring. It is like a spring. Higher their values, the more stiff is a stiffness matrix. So in that regard, there's certain similarities about this explanation related to springs. Although that these springs is not what we're interested in, because we're interested in each of the particles between these nodes. That's what we really are interested in. Okay, so that's the stiffness matrix. Mass matrix, same way, you can use your shape functions, you can integrate this over the density, you can get the stiffness matrix like shown here. By the way, there's many different ways how the stiffness matrix can be constructed. This is the one that is called consistent stiffness matrix, as it is having diagonal and off-diagonal components. But sometimes it's called, the technique that is being used is that the stiffness matrix only consists of diagonal component called lump mass matrix. And then there's a combination of these two. I don't even remember the name of these, but there's certain part, you can kind of like have 1/3 that is based on lumped, 2/3 that is based on consistent, and so on and so forth. This kind of combination exists in finite element literature. Okay, here we are. This is where we are able to express. So this is a mass multiplied by acceleration of nodal degrees of freedom, called inertial forces, but limited to small deformation with respect to your reference coordinate system. This is your elastic forces, which is stiffness matrix multiplied by nodal displacement. It's your spring, if you may. This is what you can call spring. And this is external applied forces expressed in terms of nodal degrees of freedom. How can I know that it's expressed in terms of nodal degrees of freedom? Because I'm distributing these point forces to nodes with help of shape functions. That's what the shape functions are doing to me. Again, so it's like if you have a beam element like this, and the force is applying roughly in the middle. You cannot express the force like that, because you have to play with the same game that other components in your equation of motion. And your equation of motion, you're expressing everything based on nodal degrees of freedom. This one here is in the middle. So you need to divide that to here and here. How you do this division, that's going to be clearly expressed by shape functions. Because, if it is clearly in the middle, then it's going to be f divided by 2, f divided by 2. But it can be more complicated than that. It could be located like here, and then it's not so obvious anymore. And it could be having the different direction and so on and so forth. So the way to handle it is to use your shape functions. Okay, so here it is. This is equation of motion based on finite element approach. So who died? What's up with you guys? So why is so sad? Yes, sir.
I'm wondering, when we get to the u dot dot in the other equation, why is the n not transposed anymore?
N is not transposed.
Yeah, it's changed the place with the
Yeah.
and it's not transposed anymore.
Yeah, this is I changed. Look at that. So what I did here, it would be better to be consistent because this order is now changed. So it would be better to express this component exactly the way
Yeah,
that it is here. This is inconsistent writing.
but it's the same.
It's the same, but it's inconsistent writing, but it should be different.
Okay.
Good. Very good. Anything else? Okay, this makes sense. Okay, let me summarize fast. So we start from the polynomial expansion. We express the polynomials in terms of not a degrees of freedom. We got shape functions. Then we created the relation between the displacement and strain. And this relation was, again, based on shape functions. And now we were able to create the stiffness matrix and also the mass matrix. So we were able to get inertia forces, this guy, and something that is called elastic forces. Look at this. This is a force component. Nothing but the force component because, stiffness matrix is, of course, a matrix. But this guy is a vector. Matrix multiplied by a vector is going to be a vector. So it's a force vector, like anything else. All right? And then, what we wanted to do is that we wanted to, of course, solve this one here, acceleration. And with help of the numerical integration technique, we can get the velocity and we can get the position. Oh, this is without the dot, so it's just a u. But it's not going to work out like this. It's not going to work out like this. Absolutely not. Because remember here, the body reference coordinate system that is located here, this one, in three-dimensional space, that requires 3 translational components and 3 or 4 rotational components. So that's max 7. And then this one here, typical finite-element model consists of 10,000 degrees of freedom, 100,000 degrees of freedom, sometimes more. This, if it is, let's say the minimum 10,000 degrees of freedom, 7 versus 10,000, they don't get along well. This number is that's simply way too big and takes too much capacity to solve the deformation. Because the deformation is something that, yes, it is improving the accuracy of the model. That's what it's doing for you. But the price you need to pay is way too high. This is way too much computation because look at this is so much more bigger and it's going to be hard to do this way. You need to solve this deformation, meaning 10,000 nota degrees of freedom each of the time step, and it's going to kill you. It's not going to be possible to do this way. So we need to do something. We need to do something, and what we need to do is that we need to reduce the size of this problem. That's what we wanted to do. And that's where we're going to make a use of Jussi Sopanen. We're going to move on to altogether another space. Now we're here in a nodal space, which are these points. So we're looking at how these points are moving and rotating, each of these points. That's what we're doing here. This is not good. So we need to do something a little different. Something a little different would be moving on to, these are the questions. This is something that, is it so that the next week is the last week prior to a midterm exam? Yes, it is. Okay, next week is going to be fully devoted to how you can practice yourself to midterm exam. So we're going to look each of the questions, each of them. What's going to be the way you can get the full marks from each of the questions? And again, we're going to limit ourselves the questions that you can see here in the classroom. Because I understand you guys are busy and you have a million other courses and this is complicated matters. And if I say you guys need to learn the finite element literature and multi-body literature, that's not realistic. That's going to be too much. So I want you to learn something. So let's go over these questions. Make sure that each one of you can answer the way that you can get the full points. Then you need to memorize it in certain level, make an appointment to exam. Is that the way it goes? To make an appointment in exam room?
That they had already made the appointment.
Okay. This exam is something that is new to me too. So it's the first time we try something like this.
We can expand the time, and I believe that so far 60 people they have successfully registered for the exam.
Okay, 60.
Yes.
But we have a 70 something in total
Yeah,
this
I'm
class.
afraid that if they like from this point, if the slots are filled, I can't do anything for them.
Really?
Yeah, because the seats are either we have to expand the time of it, the duration, like making it more than a week. It's not possible.
Okay.
Or I have to personally add another computer to the.
Okay.
the
All right.
exam room.
Okay. So we'll see how this gonna go. Why this exam? Because I know that. Of course, I trust you guys. I trust that you are not going to use a ChatGPT. But I'm not sure if this makes any sense because I'm an advocate of these ChatGPT and other tools. So if you have a chance to use it, use it. Use it, seriously. Makes sense to use it because it can make your learning faster. You can get the point of views that otherwise would be hard to get it. And now this exam, if you just put each of these questions to ChatGPT, you will get this. You can score a 5 out of 5. No problem. That's a little bit unfair because some of you might not be able to. I don't know if you all use it. I hope that you do. I don't even know what's the current regulation about how is it the LUT is dealing with these large language models. I don't know if there's any regulations. I don't know. Okay. Anyway, so like I said, we can get back to this next week. All right. What I wanted to say is this, and here's what I'm proposing. Let's look at this topic a little while, and then we can have a break, 5 minutes. Okay. Like what Jussi Sopanen did. He moved from one space to another, and we want to do the same. We want to do the same because we want to reduce the size of the problem. And this is the one way to make things to happen. Of course, it comes with a price. We do need to compromise the accuracy. That is correct. We are not going to get as accurate solution we were able to get if using the full set of degrees of freedom, 100,000, 10,000, whatever is a full finite element model. We do need to compromise that. Well, amount of compromisation we do is amazingly little. So it's something that we can still get acceptable solution. And again, if you're comparing this 7 versus 10,000, so we can afford to do this. And we're going to do this by moving from nodal space to something that is modal space. What relates these two spaces is assumed deformation mode. We're going to look like this time how is that the entire structure behaves, no longer a single element, but how is the entire structure behaves. And we look at the possibilities, how is that the entire structure can deform. And each of these ways that the structure can deform will be our new unknowns called modal coordinates. Now, I don't know if you can understand me because of my accent. So if I say nodal and modal, is it like no difference? All the time same. It's like coordinates. But you hear the difference. Nodal, modal. Okay. All right. So if you have a finite element model, the finite element model that consists of 10,000 degrees of freedom, what this means? It means that this finite element model that is describing a single body can deform in 10,000 different ways. 10,000 different ways. That's what it is. Because these nodal degrees of freedom are each of them like telling the ways that the structure can deform. That's a lot. 10,000 different ways. So is it really needed to be able to describe the deformation that many different ways? Typically not. Typically that's not the case. But there are this many ways. And what we can do is that instead of using 10,000 different ways, we can reduce and use a less 100, maybe 10 instead of 10,000. Why is this is possible? Because think about it. Some of them, of course, are very obvious and clear. Like if you have a beam structure, like deep beam structure, some of the modes are something like bending modes. Yes, for sure they are. But some of them are something that makes not much of a sense in reality. Like if you have an element like this is a beam structure. Each of these are nodal locations. One of the different ways could be that this node here is only moving here and rest are staying where they are. This is not very, this is hard to see that it happens in reality. It could, but I don't think it is going to be something very important. Or let's say that this one here is moving a little bit this direction, others are staying where they are. Again, I don't see that as happening much in reality. So some of these modes are less important for us. And that's what we're going to do. So again, we're going to get back to these questions. And this is the last slide before the break. Here's a cantilever beam. This is, the structure that I always wanted to explain. Simple cantilever structure. And I'm modeling this cantilever structure by using 1, 2, 3, 4, 5 elements. All right? Elements are connected together in nodal locations. So here's my first node, which is constrained to the crown. So this is something that I don't need to care. This is my first node, second, third, fourth, and fifth. Okay, if I'm using the element that I described you earlier, each of them have a 2 degrees of freedom. 2 degrees of freedom, meaning that this can move this direction and it can rotate. So that's same for each of these 4 nodal locations. So it means that this system consists of a total of 10 degrees of freedom. 10 different ways that the structure can deform. Okay, now if it is loaded like there's 0.4s in the free end of the cantilever structure, then it's quite obvious that, the deformation, going to be something that the first deformation would be like something like this. Correct. Which means that each of these nodes, they translate and rotate with respect to each other in a certain way. How much is this way? This is the structural, the behavior. How much is this way? This is something that in future I'm calling as my unknowns, my nodal coordinates that we recall as a B. Now this was a 1 deformation mode. This is going to be P1. How much this mode is like amplified. How much this mode is contributed. This amplification tells me that. And if I describe this mode numerically, it's going to be like this. Now this multiplied by this is going to give me exactly this absolute deformation. Then I can take the next one. So the next one is going to be like this or whatever. And again, is the way that the structure can deform. Where's that we can get these ways that the structure can deform? Most obvious way is to conduct an eigenvalue analysis. Eigenvalue is telling you that how is the relation between the stiffness and mass. Mass and stiffness, to be more specific. This tells you how is the vibration properties of the structure. This is an information we have already. This is an information we have too. What we're going to get as a result is these modes, these deformation modes. We still do not know these amplifications, P's, but that's okay because those are the ones that we're going to solve when we're going to move forward. All right, that's what I promised. So is it okay if it is 10 minutes? 10 minutes. 10 minutes? Why? So we kind of thought that we had a good start with a nice conversation and then it all stopped. So you use all your resources in a very beginning. What was that?
No extra points.
No extra points. Yeah, that makes sense. I like your math. So it's no extra points. Why would you communicate? Makes no sense. Waste of energy. Simple waste of energy. All right. So 5 minutes and then we will be back. Okei. Mitä puhutaan se toimii se tuo KRK, se haalarin juttu? Niin kun eka vuoden opiskelijat aina saa sen haalarin, niin onko se ihan ilmainen niille vai?
Meillä oli aina, siinä on niitä verran sponsoreita, meillä oli aina ilmainen ja
Okei.
se tulee aina vuodenvaihteen jälkeen, kun saa tuommoista laitetta.
Ei tavallaan se oli se KRK liittymismaksu, joka oli silloin
Niin.
10.
Niin se riittää. Niin se riittää.
Ja sitten se oli ne sponsorit.
Okei.
Sitten tiedän, että on kaikissa paikoissa ei ole sitä, että niinku ilmainen, vaan sitten porukka maksaa jotain.
Muillakin
Joo. Niin että se riippuu killasta.
paikassa.
Niin, varmaan paikassa vähän niin sponsorit saa. Sitten sponsorit kattamaan ne kaikki kulut.
Joo.
Vai tarvitsee vähän lisää siitä.
Missä teillä on muuten nykyään kiltahuone?
Se on siinä Lundbuffalta, kun kävelee kirjastoon päin, niin ennen kuin kirjastoon tulee portaat ylös,
Joo.
niin ennen sitä niin niitä oikealta päältä niin kuluttaa.
Siinä on sellaisia toimistoja, pari pottia, syötilapottia ja sitten
No, joo.
heti kun nousee loppupuolta ne pienet portaat.
Niin ne yhden ekan.
Ne pienet yhdet portaat, niin niitä vaan suoraan sinne
No okei, joo, kyllä mä teen tietää sen, joo. Joo.
väliin.
Oletko stökiltä aktiiveja?
Ei. Mikä
Mutta joo, kyllä mä teen tietää sen. Ne yhdet portaat ylös siinä ja se on ihan niinku...
kun tossa on toi... Tää on nyt oudosti kerroksesta. Tossa menee portaat kirjastoon, niin tossa...
Joo.
Siinä jos tulee sieltä
Se ei-
koskelta käydään ne ekat portaat ylös, no siitä sitten...
Se ei ole kauhean suuri tila. Ei ole kauhean suuri tila.
On se ihan kohtuusuuri.
Ai se on?
Se on väestönsuoja, niin
Aa,
ei siinä ole korkea sillä ole.
joo.
Joo, siinä on niinku tavallaan 2 eri pientä huonetta.
Joo.
Hyvin mahtuu.
Okay, guys, so let's continue then. All right. Now these ways structure can deform. One of the easiest way to get them is conduct an eigenvalue on us. Now comes something that is extremely important. Because in finite element equation of motion, it was like this. It's a big mess. But we started here, so we have the, again, inertial forces, elastic forces, and external applied forces. So when conducting eigenvalue, we don't care about these external applied forces. So what that means, this is a clear message to you. So if you just have a equation of motion like this, let me go back here. So if it is like mass multiplied by acceleration, stiffness matrix multiplied by displacement equal to 0. This is how you conduct an eigenvalue. Okay, because this is 0. This is telling nothing but properties of the structure. And some of the misconception that I can see every now and then is that people are expecting that these deformation modes are something that is absolute deformation that actually takes a place. No, you cannot tell that. Why? Because you need to know these modal coordinates to be able to tell that. So the mode itself is nothing but the way the structure deforms. Again, nothing but the way structure can deform. And they are associated to frequencies. Because once we conduct an eigenvalue analysis, it all becomes to be clear that there we're going to get eigenvalues, which is natural frequencies, and eigenvectors. Eigenvalues is telling me where is that the structure vibrate in a certain way, and the eigenvector tells me what is this way. That's what they are. All right, here it is. Let's look at this theoretical background, and then I have a few animations that makes clear what's the deal with this. Okay, this is what I just put it in writing in my previous slide. So is again, inertial forces, elastic forces, external applied forces are ignored. So no forces whatsoever. So this is just a structural behavior, structural properties. We do know, based on the mathematics, that there is a solution for this problem that can be written like this. Okay, forget about this detail. Focus on what you're going to get once you substitute this information to your equation of motion. You're going to get this. This consists of two unknowns. The first one is this omega power 2, which is an eigenvalues. We can get equal amount of eigenvalues than the number of degrees of freedom in your finite element model. So again, if you have finite element model that consists of 10,000, let's say 1,000 degrees of freedom, you can, in theory, get 1,000 eigenvalues, 1,000 frequencies that are telling, okay, this is where the structure behaves this way. This is how the structure behaves this way, 1,000 times. Okay. Then this one here, which you can solve once you're able to solve the eigenvalues, is an eigenvector. This is the way the structure performs. Deforms, not performs. Deforms. And of course, you don't do this analysis like explained here. This is not the way it goes, but this is for sake of simplicity explained like a little bit cutting the corners. There's a better, more efficient numerical methods to conduct an eigenvalue. We're not going to look at that. So we just look at the, what's the principle behind. And the principle behind becomes clear when you look at this solution that you get once you substitute this one here. Okay. Again, 2 points, 2 pieces. The first piece you can solve by taking determinant of the first part of the equation. And this, of course, again, you will get equal number of eigenvalues than the number of degrees of freedom. Once you have solved them all, then one at a time, you can substitute it here, and you can solve the corresponding eigenvector. That's how it goes. Let's look at the simple example, and then it becomes to be clear. But prior to that, finite-Selman model depicted below consists of n number of elements, n number of degrees of freedom. I don't know if this was clear based on my explanation. I think that it was clear. N number of degrees of freedom. The model can be solved by using question mark number of eigenvalues. What is it? Is it going to be equal to the number of elements? Is it going to be equal to the number of nodal degrees of freedom? Is it going to be elements minus the nodal degrees of freedom? Is it going to be elements plus nodal degrees of freedom? And again, this was elements. One only is correct. Which one is correct? Which one is correct? I don't know what the others are saying. You agree or you don't? You do not agree. Okay, so let me take myself back here. I'm going to clean this PowerPoint presentation, so if I need to go back, it's going to be more easier to do so. And it was this one. Okay, so, okay, guys. You cannot see this. How is it in YouTube? Still no. No, it comes. How is it in YouTube?
It's fine.
It's fine. Okay, what's the success rate of this first in-class quiz of the day? Look at this. I'm very, very happy. This is what makes me happy. Look at the number of participants. 52. That's really good. Okay, but what's the success rate? 75. 75%. I'm saying 75. 80? So I'm saying there's 75 or below, or below, or below. Oh my God. You guys, I don't think that I trust you. You said that you have no ways to communicate. I'm sure you do. I'm sure there is some kind of like a WhatsApp group or something that is going hot every single time we go these questions. Okay, next one. Online. But you guys are not aware of this thing. Okay, then you shouldn't come here. Okay. Finite-Selman depicted below consists of n number of elements. S is missing here. N degrees of freedom. The model can be used to solve n number of eigenvalues. So which one it is correct one? Which one is correct? Okay. I'm going to let you think this, and I'm going to jump back because I just realized that it's already 25 past 11. Look at that. And the next week we need to focus on exam thing. Yeah. Slow, a little bit slow. Okay, what is this eigenvalues? What's a physical interpretation of eigenvalue? So this is something that, not this order, this order. Okay, the eigenvalue, physical interpretation of that is something that if you have like spring and mass system that I'm going to depict here. So if you have a system like this, so there's one spring, one mass, and you excite the system by a force where the force is a function of time. And the function of time is going to be something like this is time, this is force, this frequency can change. The force can have an amplitude and it can have a frequency. This is how you measure the frequency, like what's the difference between two neighboring peaks. This is something that I can adjust. And once I adjust these forces, it is possible that this frequency hits the frequency that is Aiken, that is coming from as an eigenvalue analysis. So it's a frequency that is a structural frequency too. So then they becomes to be in the same frequency. And this is something that is called resonance condition. A resonance condition is very, very bad because in theory, amplitude of this mass started to become to be infinite. It's not going to be infinite in reality, but in, theoretically, if you look at what happens when you have the resonance, it becomes to be like this. And you see the resonances all over. You see that, every now and then there's a small piece that is making an awful lot of noise, more than it's supposed to make. And this is because of the resonance condition. Now, the system that I'm describing here consists of one mass, one spring. So this is a 1 degree of freedom. If you have two masses, two springs, and then this is connected to ground. This can have two resonance conditions. So these two resonance conditions are different. And again, you can make it vibrate in this way by just testing how it is loaded. So that's what it is. So here's just to make sure that we understand what this is about. I want to show you. I cannot show you this animation. No, not willing to do it. Should I put it like this one? No.
Can you exit the full screen?
And then go back. Look at that. So they disappeared. Okay, what I need to do, I need to send you a link. But these animations these are actually YouTube videos about, excuse me. Let me take this back one more time, like this.
Because this morning I could see them.
You were able to see it, seriously.
I opened them in the software.
So you were able to see them.
Yeah.
Okay, I'm going to send you a link, so take a look at them. So this shows like how is this deformation of the system that consists of like 1, 2, 3, 4 nodal coordinates, kind of nodal coordinates. So you can see what are the different resonance conditions and how they appears to be. And this is demonstrating the same thing. This is just relating this eigenvalue analysis to vibration analysis, which I'm sure that you guys are already familiar with. Something that uses up and explains over and over again. And here is a little bit in this direction. Okay, so wanted to take a look at them by yourself, and then look at that. So now it is actually doing something because my presentation is stopped. No. Okay, let me skip that and go directly to this one. All right, what we learned. So we learned this, that we can get equal number of eigenvalues than the number of degrees of freedom. This was something that was in class quiz. Okay, how they look? Let's take a look at a few animations. So this is, you don't see this. Let me see if I can make this in a fly, duplicate. So here's an animation that shows different kind of natural frequencies and corresponding eigenvalues. And look at this, look at the numbers. So this is like a 279 hertz. And you see that, higher you go with your frequencies, the more and more complicated this deformation modes becomes to be. And look, we're still using very limited number of freedom. Really limited number of deformation modes. They are much more than we're just displaying here. But you see that they becomes to be more and more excited higher we go with these natural frequencies. And here's something that we can make a use. Like I said earlier, some of them are not contributing much. And it's actually very common that one of the first frequencies are contributing the most of their deformation. And the rest, the contribution is insignificant. And this is what happens in nature. The ones that are, if you have a, group of animals, The ones that are contributing the most are the most strongest. And those are the ones that make sense to keep it in your team. Others, you can get rid of them. Same here in eigenvalue analysis. The ones that are not contributing much, you can let them go. You can say, I don't care about you guys because your contribution to this final solution is insignificant. I don't care about you. Go away. And when you do that, yes, you are compromising their accuracy a little bit, but not much. Not much. It's very common that happens like this. Like if you, because you can, each of these deformation modes, you can easily compute something that is called strain energy, and how much they contribute in the strain energy for entire deformation of the structure. Let me see if this goes correctly. No. So every single time that this cable is connected, so it's not willing to go well, like this. Okay. Let me see if this is willing to. Something is off in this presentation now because it keeps stucking all the time. Is it like there is too much? And look at that. Somehow this display system is not.
When was the last time you turned off, you shut down your computer?
Oh yeah, it was actually last year. So it was last year, not this year, but last year.
Seriously?
Yes. I usually don't turn off my computer. No, it's not willing to draw anymore. I need to make this drawing a little later. Oh yeah, all is happening here. Now, okay, so here is something that is like each of these modes based on their natural frequency. This is mode number 1, mode number 2, mode number 3, so on and so forth, and it goes all the way to 10,000. And this is a strain energy, like how much they actually contribute in the strain energy that can be computed like this. Okay, how much they contribution to actual deformation as energy perspective. It's very common that could be the case that the first one is contributing very little. Second one is contributing like 80% of the max. Then this one is 10%. And somewhere, then there could be here is one more, like 5%. And the rest is like 0.0000%. And if it is 0.000%, it doesn't make much of a difference. So you can easily ignore them. And that's exactly what is being made in model reduction technique. So the ones that are contributing very little, are just you just let them go. You don't care about that. And that's how you can come down from 10,000 degrees of freedom to whatever number you want. And it's amazing that often 10 is enough. Then it is giving you 98% of the strain energy, which is a good estimation. It is true, you're losing 2%, but that's still okay.
So can you repeat what's on the y-axis?
Y-axis?
Yeah, y-axis 0.002.
Yeah, this is strain energy.
Okay.
Strain energy. And sorry that this is a little bit unclear, but I wanted to say like this equation. 1 divided by 2, this is what it is. So that's the strain energy. Okay, how much, because each of these modes, I can compute how much they are producing strain. And when I'm comparing that to entire strain of the structure, I can see the percentages. And it's, of course, this is hypothetical graph, but it's common that one of them is like the one that is mainly responsible of the strain energy, 80%, 50%, more than that. The rest could be very insignificant. And then the ones that are very, very small, like super insignificant, you can get rid of them. And the damage you're going to get in terms of accuracy, not much. Yes, you still get an accuracy damage, that is correct. But let's look at something like this one. Of course, if you think about this kind of the deformation, this is extremely important if you have a loading in a direction of transverse loading of like horizontal loading direction. Extremely important. If you have a loading in another direction, this kind of deformation mode, you definitely do need to keep with your computer. Otherwise, your accuracy will go down significantly. Probably this one too. But the higher you go with your modes, more exotic they becomes to be. This is a deformation mode where the frequency is already more close to 3000 hertz. And yeah, maybe this could be something that you are interested in. But then this is super exotic. The frequency is 12,000 hertz, close to that. Do you think this kind of deformation makes a difference in your life? No, it doesn't make a difference in your life. Get rid of it. And what you're gonna get is more efficient computing, and the damage in terms of accuracy is insignificant. I don't even know how you can load structure like this, with the magnets of course, but seriously, this is not happening. This could be important, this could be something that yes, it can take a place in reality. This for sure not. And this is what you can use in model reduction technique. Now comes something beautiful. I remember when I was in your age, and the professor that was explaining this model reduction at the time, when he explained this slide, it wasn't this slide because it wasn't this technology based on the PowerPoint, but it was overhead projector. He was crying because he said that it's so beautiful. It's one of the wonders of the world. I don't know if it is really that big deal, but he was very emotional when he was explaining it. So if you feel to cry, it's okay. It's okay. Okay, so what we can do when we're moving from nodal coordinates to modal coordinates. This is our original equation of motion. Okay, and we have the relation that I explained earlier. So relation is this. So we are replacing the nodal coordinates by modes. We're going to take a look at the example, like how these modes actually look like. And then we have a certain number of modal coordinates. And let's say that this is not exactly equal, but is roughly an estimate, meaning that this vector can consist of this original 10,000 degrees of freedom we discussed earlier. This one is only 10 degrees of freedom. Okay, what happens when we do that? Now this one here is a matrix that consists of these deformation ways, the way the structure can deform. And these are corresponding amplifications. Now when I substitute this information here, the equation can be written like this. P dot dot, because this is a linear relation, so it goes like this. And then this is a stiffness. P is equal than forces. I'm not going to take these shape functions into account. This is still not okay because you look at I have here modal coordinates as an unknown, but the forces are still expressed in terms of nodal coordinates. So I need to convert that to be in a modal coordinates. And the way can I make it happen is that I multiply entire equation both sides by transpose of the shape function matrix. Now what happens when you do that? It's going to be like this. P dot dot, and then this is going to be transpose. I don't know if you can still see well in my writing. And then this is transpose force. Now that comes with the two major consequences. First of all, the size of your problem is significantly reduced because this matrix is now 10 times 10 when it was originally 10,000 times 10,000. So it's significantly less than it was. And there's another, and this is where my professor at the time started to cry. There's another major consequence. And the major consequence is this, that if these deformation modes are orthogonal, as they are if they're coming from an eigenvalue analysis, then off-diagonal components of this new matrix disappears. You get diagonal representation, meaning that each of these modal coordinates can be solved independently. You can just take any modes you want, solve it without knowing nothing at all about others. And that's another beautiful, beautiful consequence of this reduction technique. Here too, this, by the way, is of course there's supposed to be this matrix here. This too is going to be diagonal because this matrix is an orthogonal in nature. Okay, so when you do that, when you scale these modes in a proper way, you can have a mass matrix that is an identity matrix, meaning that diagonal components are equal. The zero off-diagonal components are diagonal components are ones, off-diagonal components are zeros, and then when you do the scaling like that, the stiffness matrix is going to be something that eigenvalues appears to be in a diagonal components. This depends how you scale, because you can scale these modes the way you want. Okay, let me see. Let's look at this example. We're going to redo this example next week, and then we're going to stop. How that sounds? Okay, I'm still going to sit to explain this example to you. Now I'm going to go back to the simple example about the spring element. So this is a spring element that consists of 1, 2, 3, 4 nodal points. And each of the nodal points have 1 degree of freedom. So that's the structure, that's what it is. So this consists of 1, 2, 3 elements in total. Okay? So what I'm going to do is that I'm first constructing the stiffness matrix describing this entire structure. This is something we have not discussed, but you can describe that by overlapping the stiffness elements and mass elements in such the way that this one here is going to be associated with the first element here. This one here is going to be associated to second, and the one here is going to be associated to third. You see that they are overlapping in these points. And this is the way you can combine the structure to be combined. Otherwise, they will be separated and they have no relation whatsoever. Same you can do for a mass matrix. Okay? Now, look at the dimensions. So I have here 4 rows, 4 columns. 4 columns, 4 rows. And they're skewer size matrices. Okay, so let's put them in this equation that we looked earlier. Let's first compute the eigenvalues. I don't know why, but I obviously want to make you feel confused, because instead of using omega 2, I'm calling here lambda. But don't get confused. This, of course, is the same thing. Of course, they are the same thing. And of course, I'm not computing this numerically the way that I do it here, but I just want to demonstrate how it goes. I'm going to take a determinant of the matrix where this is a stiffness and this is a mass. A mass is multiplied by eigenvalues. Okay? When I take a determinant of that, I'm going to take the polynomial as it is shown here. You see that this is a 4th order polynomial. How I know that? Because this lambda is multiplied by this lambda. Here's a lambda again and again. So it's a 4 times. So it's a 4th order polynomial. How many times this will pass 0? 4 times. And when I solve them, I'm going to get the numbers like shown here. Lambda that is equal to 0, 12, 60, 140. Very standard thing. So some of them are very small, some of them are very big. What is this 0? Eigenvalue equal to 0. Static? Very good, very good. I've been asking this in other years too, and there have been no occasion that anyone is able to answer. A few occasions that somebody is able to answer, what's this 0? You said that this is static. Okay, it is because of my model. This one here is not connected anywhere at all. This is rigid body motion. You were about to say rigid body motion. I knew it because you were about to say like and then I say rigid body motion. So it's like when it's moving like this, because nothing stops it doing so. When you do this, then there is no deformation. It's just traveling back and forth like this. The rest is obviously associated to deformation, as is a third and as it is a 4th. How is that I can see what kind of deformation? Well, again, I can take each of these values, substitute at this equation, and look how is the way that they can deform. Okay, I can put 12 here, and then it gives me 4 equations, 4 unknowns. 4 unknowns will be these 4 nodal locations. How is that they moving with respect to each other? And if I solve them for value 12, I'm going to get these ones. So if my original element is like this, first one is moving minus direction. So let's think that, okay, the minus direction is going to be like here. The second one is moving a little bit like here, and here. That could be the deformation. So it's like simple motion like this. How much? This is something that we don't know. Why not? Because this is just the way they deform. And what is a funny thing? These numbers you can multiply by any number you want, and they're still going to fulfill this equation, this original equation. Multiplying them by any number you want is called scaling. Sometimes it makes sense to scale these numbers such that, because computers, what they love is numbers that are close to 1. Closer the better. Sometimes these values can have a very small numerical values as a consequence of which some of these diagonal components, when you look at this one, where was it? These can be inconvenient numbers for computational purposes. And now with the scaling, you can make them to be more pleasant to deal with. So it doesn't make any difference really. It's just that it's more convenient to deal with. Same package, it can be big or small, it's your decision to make. All right, so we got this 12, this is the vector. The fourth one was like this. So it was meaning like if it is originally like this, the first one was moving this direction, second one was moving this direction, this one this direction. So it's like wave traveling within the structure. This is what it is. So example about eigenvalue analysis. All right, this is where I'm going to stop because we need to rush ourselves to go to have lunch. Physical interpretation of eigenvector. Okay, relative displacement of nodal degrees of freedom. Absolute displacement of nodal degrees of freedom. Strain distribution within the structure. No clear interpretation. Which one is correct? Okay. Okay. Just a second, you don't see this, but momentarily you will. Okay, success rate of the second in-class quiz is... No, okay, here it is. Success rate, 75. 75 again, because it's, I'm suspicious, like how it can be this high. This time, oh my...
For sure.
Take a picture, take a picture. Hold on, I need to scroll this up a little bit. It's, oh, okay, so you don't, okay.
It's locked.
It's locked.
Yeah.
Here's a camera. Very nice, 100%. If I would be in social media, I would definitely post this to my social media. Problem is that I'm not. Okay, next one. This is the last one, and then we're going to go. Physical interpretation of eigenvector. Once you're done with that, then you can go. Lunch is next. Lunch will be next stop. Any comments from online participants? No. No comments. Okay, thanks guys. See you next week. And next week is a important week as we're going to practice ourselves to midterm exam. Be there. Okay, take it easy. See you guys.
So have you stopped streaming?
No, but I will do it now.